In this talk, I'd like to tell you about this paper on directed isoperimetry and monotonicity testing, and in particular the connection between these two concepts. So I'm going to start the talk by telling you about a little bit about isoperimetry and then how it connects to monotonicity. So to tell you about isoperimetry, I want to talk about this Poincaré inequality. A Poincaré inequality is a type of local to global inequality in the following sense. So fix some domain in Euclidean space, some parameter p that doesn't matter too much, and then some smooth enough function f, whose mean is f sub omega. The inequality says that the distance from f to its average in LP norm is at most some constant times the norm of its gradient. So the way to interpret this is that the left-hand side is a distance to a constant function, and the right-hand side is the integral, it's the total amount of the local violations of this property of being a constant function, because the gradient is non-zero when the function is locally non-constant. Okay, so that's the inequality. This inequality is very widely studied, has long history and many connections. It started with Poincaré himself studying partial differential equations, PDEs, that arise in mathematical physics. In particular, it characterizes something about the convergence of the heat equation, and I'm going to go back to that. If you choose different parameters like p equals 1, it also characterizes something called the isoperimetric constant of your domain, and is connected to expander graphs and Shiger inequalities, for example, and many more connections in mathematical physics, in geometry, probability theory, and so on. Okay, so this is a very important concept. Now, for the second component of this talk is the algorithmic task monotonicity testing, which is a central problem in this field of property testing. So in property testing, we want to distinguish whether an object X has some property P, or if it's epsilon far from having the property, meaning that it has to change a lot in order to have the property. And we want our algorithm to detect which of these cases we're in using very few queries to X. So we want to minimize the query complexity. That's the algorithmic setting here. And the problem of monotonicity testing is the problem where you have a function on some partially ordered domain, and we want it to be the case that whenever X is below Y in the partial order, f of X is the most f of Y. So this problem has been studied for over 2 decades now in many settings. Perhaps the most classic setting is the fully Boolean case of Boolean functions in the Boolean hypercube, but you also have real value functions on the hypergrid. You can have general posets. You can have continuous setting, for example, the d-dimensional solid cube and real value functions, and this particular is the setting of this work here. And in addition to various algorithms and upper bounds, we also have many lower bounds for all of these settings, but this talk is mostly about upper bounds. And in particular, I'm going to talk mostly about the Boolean setting as their comparison points, and then the continuous setting as the contribution of this work. So as a warm-up, I'm going to tell you about one algorithm for testing monotonicity of Boolean functions in the Boolean cube, and why it starts revealing this connection between monotonicity and isoperimetry. So let me tell you about this very natural tester called the edge tester on the Boolean cube. What it does is the following. It samples a uniformly random edge from X to Y, so Y is obtained by flipping one bit of X from 0 to 1, and it rejects if that edge violates monotonicity, meaning that f of X is greater than f of Y. So this tester never rejects monotone functions, but the question is, if the function is far from monotone, epsilon far, how many queries do I need in order to reject with some good constant probability? And the classic lemma about the edge tester, which answers this question, says the following. If f is epsilon far, then v of f, which is the number of violating edges of f, is at least epsilon times 2 to the d. So taking this for granted, it turns out that the success probability of this tester, the rejection probability, by calculation, is essentially epsilon over d, which means that d over epsilon queries suffice. So this is a nice classic result about the edge tester. And my claim in terms of the connection to isoperimetry is that this lemma is actually hiding a Poincaré inequality just restated. So let me convince you of this claim. So here's the lemma restated, and recall that from the first slide, a Poincaré inequality has this form over here. And I'm going to rewrite this inequality just by replacing the left-hand side. Instead of writing distance to this average, I'm going to just use this notation here that I'm going to explain in the next slide, but it means the LP distance to a constant function, and this is at most the expected norm to the pth power of the gradient of f. Okay, so I'm just writing what a Poincaré inequality is in different terms. Now, in this Boolean setting, I need to tell you what a gradient means, and it just means a discrete gradient. So for example, for this point y here, it is -1 on the first coordinate because this edge is decreasing from 1 to 0, and it is 1 on the second coordinate because this edge here is increasing from 0 to 1. So that's a discrete gradient. And then I'm going to use this notation gradient minus, which is the minimum between the gradient and 0 entry-wise, to denote the directed gradient. So notice that the directed gradient only preserves the violating edges. For example, here for point y, it only preserves -1, which corresponds to this violating edge. This edge violates monotonicity. And then if you take the inequality of the lemma and you just normalize by dividing by 2 to the d on both sides, you're left with epsilon, which is the distance to monotonicity on one side, and then on the other side, the average degree of violating edges. And this is just a different way of saying this right-hand side quantity here, which is the expected L1 norm of this directed gradient. So this is the number of violating edges incident to a particular point. So it turns out that this lemma is indeed giving us a directed Poincare inequality, because if you compare the Poincare inequality here to the inequality here, I'm replacing distance to constant functions with distance to monotone functions, and I'm replacing gradient with directed gradient. Now, let me give you a little bit of notation before I can tell you that this connection is not limited to this one lemma, but is actually very deep and very important for this problem. So I'm going to generalize the type of inequality that I've shown you so far. So for parameters P and Q fixed, which essentially are going to give us different flavors of inequalities by changing the order of integration and changing the geometry in which I measure these vectors. Don't worry about the technical details too much, but I'm going to say that a Poincare inequality for parameters P and Q is something like this. So it's telling that the distance to a constant function in LP norm to the pth power is at most this expected Q norm of these gradients also to the pth power. So that's a general type of inequality. And then I'm going to say that a directed version of this inequality is the same thing, but now I'm measuring distance to monotone functions, and I'm only going to take into account the directed gradient, so these negative entries that violate monotonicity. And just to be precise here, distance to a constant function means the minimum distance to any constant function, and distance to monotonicity means the minimum distance to any monotone function. And the gist here to take away is that these inequalities are connections between local violations of a property of interest, constant or monotone, and, sorry, on the right-hand side, I have the local violations, and on the left-hand side, I have the distance to the property of interest. Okay? So this is the type of result that we like in property testing. Now let me show you this map, which essentially plots this depth and breadth of connection between monotonicity testing, directed isoperimetric inequalities, in particular directed Poincare inequalities, and the classical versions of these inequalities. So without listing all of the developments, let me just tell you that here in this discrete column, which is talking about the fully Boolean setting, what I just told you about the edge tester was that an L1 Poincare inequality in the directed sense implies this linear query complexity for the tester, d over epsilon query suffice. And it turns out that you can extend this connection between Poincare inequalities and directed versions in monotonicity testing much further. This type of connection was first observed by Chakrabarty and Seshadri, who got the first sublinear query complexity tester. And the state of the art here is the optimal non-adaptive tester, which is a square root of D tester by Cotman and Zirasafra. And it turns out that this follows from the directive version of another Poincare inequality called Talleyrand's inequality. So that's all for the Boolean case. Now, isoperimetry is also very, very well understood and studied in immense depth in the continuous setting, because we really started with mathematical physics with Poincare, as I told you. And we can get at least a first connection to monotonicity testing in this case. I showed this in a paper last year by proving that a directed version of a L1 inequality, same as the edge tester here, gives us a tester with linear query complexity in the dimension D. So again, same as the edge tester. Now, if this connection between isoperimetry and monotonicity testing is really fundamental and there's some underlying fundamental principle behind it, what I would expect is that the most classic, well-understood form of the classical Poincare inequality, which is, it turns out, this L2 inequality, the one that Poincare himself was studying, the one that you can get from Fourier analysis and so on, may also have a directed counterpart and perhaps imply something about monotonicity testing. And in particular, if we could get something that is a sublinear query complexity tester, mirroring the discrete developments in the continuous world, then that would really strengthen this connection. And that is particularly the aim of this work. So the results in this work are precisely a L2 directed inequality, which is the natural equivalent of the most well-understood classical inequality. And then that implies a square root D query complexity tester, which is what we were after. So before I can tell you these results in a little bit more detail, let me tell you the overall goals of this talk, and then I'll dive into the model. So the goal of the talk is, first of all, to give you an idea behind what this square root D tester is doing once we assume the directed Poincare inequality. And then I'm going to give you some flavors for the proof of the directed Poincare inequality, in particular by telling you, one, about this partial differential equation, this PDE called the directed heat equation that turned out to be a very central ingredient for my proof. and in particular, why should we study a PDE in order to understand an algorithmic task. And then I'm going to tell you about one ingredient that was very important, which is optimal transport. And it seems like optimal transport was a very helpful tool for tensorizing an inequality, taking a one-dimensional inequality and transporting it to a d-dimensional inequality without losing anything in the dimension, which is something that we often want in TCS. Okay, so what is the testing model so that my algorithmic results can be placed in the proper context? So because we are in the real valued setting, we need to define our model carefully. And in particular, we're going to be studying the LP testing model that was introduced by Berman, Raskolnikova, and Yaroslavtsev. So we're measuring distances in LP sense. And we need to assume something about these real value functions, and I'm gonna assume that they are Lipschitz, which is the same regularity assumption as the previous work in this setting. So my input is an M Lipschitz function on the solid cube. I want to accept if it's monotone and reject if it's far from monotone, at least epsilon far, in L2 sense. And in terms of my access to the function, the usual type of access that is most commonly considered in property testing is a value oracle, where I can give a point x and get back the value f of x. It turns out that for this work, it's more convenient to assume this directional derivative query, where I give it a point x, a direction v, so that's a vector, and I get back this directional derivative, which is the inner product between v and the gradient. And if this seems too scary, let me just tell you without going into details that under reasonable assumptions about the function, how smooth it is, you can actually simulate the second oracle using the value oracle. So this is, I claim, not too powerful, not too scary. And as I said, the prior work in this setting gave a linear query complexity tester. So our main open question was, do we have a sublinear tester? And I'm going to say yes. So what are the results in this paper? First, I show a directed Poincare inequality in this L2 variety. So I say that this is monotonicity in L2 sense squared is at most this squared L2 norm, squared Euclidean norm of the directed gradients of f. Okay, so this is the directed Poincare inequality. And then the monotonicity testing result is that in the model that I just presented, we do have a tester with square root d query complexity, and then I pay this factor m squared over epsilon squared. And then the only other thing I want to say about the result is that this square root d dependence, I don't know if it's tied for any type of tester, but for the type of tester that we give, and in particular for this continuous generalization of the so-called pair testers from the discrete setting, square root d is optimal. So if you want to do better, you need a tester that does something different from what we do. Okay, so I want to just tell you a little bit about how this tester works. The tester is very simple. It picks a point uniformly random in the cube, and it picks a direction v that is going to be coming from certain distribution that I'll tell you about in a second, and it rejects if and only if f is decreasing in the direction v. Okay, so it's similar to the edge tester in that sense. It tries to find a place where f is violating monotonicity. And why does this tester work? So I'm going to give you a black box lemma that is proved in the paper and then explain why the tester works. So the lemma says the following. If I'm trying to detect the fact that this gradient here has a negative entry by picking a direction v that is the most favorable possible, that helps me detect by getting this negative inner product, then it says that there's a distribution d over this vector, and in particular is going to be just a binary vector, just picking subsets of coordinates, such that the probability that I detect this negative inner product is at least bounded by the following quantity. So first I have this ratio between, in the squared sense, the total kind of weight of the negative entries compared to the total weight of all the entries. So I have to pay something about this factor. And then I also lose something about the dimension d. I lose the square root d log d factor, okay? But it's not linear in d. My loss is only square roots. This is the important point about this lemma. Now, taking this lemma for granted, and let me just tell you that looks informally like a signed version of the group testing problem, if you're familiar with that, because I'm trying to detect something about the entries by doing these broad kind of dot product type queries or subset sums. And taking this lemma for granted, why does it give us a testing result? Well, my rejection probability when my function is far from monotone under this tester is going to be the probability that my inner product is negative, which using the lemma is going to be the expected value of this expression over here. But then my squared norm of the gradient by the Lipschitz assumption is at most m squared. So I'm left with the expected norm of the negative components of the gradient. But by the Poincare inequality, this is at least my squared distance to monotonicity, which is epsilon squared. So this is exactly the shape that I wanted for my query complexity, and we're done. So this is what I wanted to say about the tester. Now I'm going to give you just a few proof ideas, basically a flavor for the takeaways that I care about for the proof of the Poincare inequality. So the Poincare inequality is intimately connected with the heat equation which says the following. For a given function on the continuous space, and then think of function u as a function of time and space, so t is time and x is space, the heat equation says that it's changing as follows. The rate of change in time is equal to the Laplacian, which is the sum of the second derivatives of u. And if I specialize this to one dimension only, I'm saying that the rate of change is equal to the second derivative of u. Now, this is a picture of the initial states, and the arrows here are kind of pointing to how mass is moving as this function converges toward equilibrium, toward this average. And let me just show you an animation for how this proceeds. So this is what a heat equation does. Okay, it quickly makes the function converge to this average value. So all right, this is the heat equation. Now, why is this relevant for us? Well, it turns out that first of all, the Poincare inequality is very, very closely connected to the heat equation. And in particular, it characterizes by this equivalence here that I'm not going to go into too much detail, but it characterizes how fast the variance decays. So it converges to equilibrium as fast as the Poincare inequality allows you to. And there's a different quantity called the Dirichlet energy that also decays exponentially. And it is written in this way here, where I'm integrating all of the square derivatives. And the point is that this energy here is essentially adding up the local violations of the property of being a constant function. And the Poincare inequality says that this decays exponentially. Now, in order to understand the monotonicity problem, I'm going to tweak this equation in order to get something that converges to a monotone function instead of a constant function. So basically, I'm going to put this minus sign here, meaning I only care about the negative components of the derivative, which essentially means that the particles here, the mass, is only allowed to move to the right, so that I want it to converge to something that looks like this red function here. And indeed, let me just show you an animation of what this PDE does. So this is what the directed heat equation does. It's fixing all of these non-monotone regions, making them converge toward equilibrium, and basically leaving this region alone because it doesn't have to change. Okay, so this is the directed heat equation. And we hope that since it converges to something monotone, that we're going to learn about the distance to monotonicity. And I want to analyze it via the directed Dirichlet energy, which is just considering the negative components of the derivative, which are precisely the violations of the monotonicity property. And I hope that this decays exponentially, as it does in the classical sense. And without giving you more technical details here, it turns out that yes, it decays exponentially. The main tool that we use to analyze this PDE is gradient flows. And the proof gets pretty technical because this is a nonlinear PDE, but that's the main idea. Now, why does this help us? Well, it helps us because this PDE, using the exponential decay, is going to give us an inequality, is going to give us a bound in terms of an optimal transport distance called the Wasserstein distance. So the Wasserstein distance basically tells us to go from some measure ρ0 to some measure ρ1. What is the minimum cost of going from ρ0 to ρ1, where moving mass from some point x to some point y costs the squared Euclidean distance from x to y. It turns out that because of the decay of exponential decay in energy, I can derive something called the transport energy inequality, which says that if my violations are small, then my Wasserstein distance to the equilibrium, to the monotone function, is also small. And the advantage of getting this inequality is that tensorizing it to multiple dimensions is easy thanks to the Pythagorean theorem. Because if I moved some squared horizontal distance and some squared vertical distance, then the Pythagorean theorem tells me that the squared distance overall is in most the sum of those two quantities. So I can immediately get a tensorized version of this inequality for d dimensions. And that was the key point here, because tensorizing is usually hard. Now, once I got this tensorized inequality, it's not too hard using something called Kantorovich duality. I need to do some technical work, then I'm not going to go into details, but it turns out that basically adapting standard theory, we can recover a directed Poincare inequality. So basically replacing the left-hand side, which is Wasserstein distance, with LP distance, which is what I wanted from a Poincare inequality, and that gives us the proof of the directed Poincare inequality. So just for some conclusions here, we have extended the connection between directed isoperimetry and monotonicity testing to the continuous setting. The fact that we got a square root D tester helps to bring us closer to the developments in the discrete world. And the takeaway here is one, that somehow this convergence of a PDE is telling us something about the monotonicity problem and the connection between classical and directed Poincare inequalities. And that optimal transport turned out to be a very useful ingredient for tensorizing these inequalities. So some open questions are, first of all, our tester is very similar to the path tester, which came from that KMS paper that I told you about, but I don't know if there's a formal connection between these two. That's an interesting question. I also don't know how to show lower bounds for general testers in this continuous setting, and I would also be interested in more applications of this type of dynamical approach, this PDE and optimal transport, to other problems in property testing or even more broadly in TCS. So that's what I want to leave you with. Thank you very much.